Okay, so next we will introduce how to use shared memory. Okay, so as we already said, shared memory is pretty fast. It's almost as fast as the register. That's why if you have any data that will be reused and coming from the host, you should consider to use a shared memory, right? Because it's a programmable cache, so you can always store the data you want in the shared memory, and to have a performance as fast as the register. Okay, but it has the limitation. First of all, it can only access by the thread within the same thread block, right? So how to partition your threads become important. It will determine whether they can access the same shared memory content or not. The other one is you have only limited space again for the shared memory, so you have to use it well, and sometimes you have to move your data from the global memory to the shared memory in several iterations or iteratively. Okay. All right, and the size, as we mentioned, the size of the shared memory again is limited by the thread block. Okay, so there's an upper limit for the shared memory size per block, and you can find that by checking out the compute capability, or you can use the device query or the device query command. It will tells you how many shared memory can be allocated or assigned to each thread block on your GPU. Okay, usually the space is not much. Okay, probably just a couple of kilobytes, and the reason it's not a lot, not just because kilobyte is not considered to be a huge space, but also because the space needs to be shared among all the threads of the block, right, of the thread block. So again, if you have more threads within the thread block, then each thread probably can only assign or manage fewer number of bytes, right? So again, usually this is another reason why the size of the thread block is limited in terms of the performance. If too large, you will suffer from those memory delay for your local variable as well as for your data stored on shared memory. And by the way, this shared memory is stored on the on-chip memory, right? And we said that L1 cache for the local memory, or for some of those global memory cache as well, are also stored on shared mem on the on-chip memory. So in the past, actually, all those cache and shared memory, they use the same chunk of on-chip memory. So you can configure the ratio among them, okay, to decide how much space is available for shared memory, how much memory is on-chip memory is available for L1 cache. That's in the past, because in the new architecture, we have increased the amount of memory we have on the hardware. So nowadays, those memory usually managed independently and have their own memory space. Okay? So you don't need to worry about that trade-off anymore. Okay? But anyway, still the size of the shared memory is pretty limited. Okay? All right. So since it's limited, right? So but still it's important for optimization. Actually, it's the most important thing for optimization. So in general, as we know, the data is coming from the host, so we move it to the right persistently stored on the global memory. And when you need to be accessed by the core, you can access on the global memory directly, but you will be slow. Or you can move the data to the shared memory, then you can benefit from the much faster data access time. Okay, but because you have limited space on the shared memory, so sometimes you have to decide, you have to process those data chunk, maybe we should say data chunk, one by one, right? Partition your data on the global memory to several chunks, which you can feed each chunk to each shared memory space, and you have to iteratively process through those data chunks. Okay? And as you can see, because shared memory access is much faster, so if you can reuse the data, then you will definitely benefit from shared memory. On the other hand, if your data access pattern does not try to reuse the data, then you probably don't want to move the data to shared memory, but because you won't get any benefit in the future, right? And you actually perform an extra copy, extra data access from global memory to shared memory, and then from shared memory to the core. So if there's no data reuse pattern, then you don't need to use the shared memory. All right, and of course, the shared memory content needs to be write back, right? So once it's stored in the shared memory, then you can repeatedly access it, right? With much higher data access speed. And how to access it, as we will introduce later. Okay, so basically, again, you want to serialize your access pattern, so you can benefit from a technique we call the uh, closed memory access. Okay, basically the same technique like the collective I/O we introduced for MPI programming, but that's at the software level, right? In GPU on the shared memory, we have those. We also have similar type of I/O optimization, but it's done by the hardware, and it is called the closed memory access. Again, we will introduce that in the next lecture. Okay. All right. So the access pattern on the shared memory also matters. Okay, and we will talk about that more later. Okay, and after you finish manipulate on those data stored in the shared memory, then you still have to write it out, right? Because the data in the shared memory is not persistent. Once the thread block is finished, then the shared memory space will be freed. So if we want to keep the result, we have to write it back to global memory because it's persistent with respect to the process or the program you run on GPU. So usually you want to keep the data and store it in the global memory. Also because you can only move the data from the global memory to the host memory, right? The CUDA API at the host side does not allow you to directly access the data stored in the shared memory. So you still have to dump or write the data from the shared memory to the global memory before the data can be moved to the host memory. Okay? So you can see there is a data movement overhead for using shared memory. So again, there's a trade-off. It all depends on your computation behavior and data access behavior. Okay? All right, so let's take a look at how the shared memory can improve our computing performance. Okay, and this is a simple example, that you have seen it before, if you remember. When we introduced the CUDA programming, we introduced a CUDA code for computing the all-pair shortest path. If you don't remember, it's okay because this is the code for that. Okay. And what we care about is the data access behavior in this program. Okay. So this is a kernel code, right? And you should already know that the variable, the matrix D, is stored on the global memory or on the device memory, because that's the spec, right? The kernel function can only the argument of the kernel function has to be a device pointer, right? Some memory allocated on device memory, on global memory. Okay. And if at that time we didn't introduce shared memory, right? So if you look at the code, you can see that there's no for loop in the kernel function. So you can easily see that in the computation, each thread supposed to access the global memory 6 times. Because every time you try to read or write, right, to access the D matrix, that means access to the global memory. Okay, so in total there could be 6, right, memory access on global memory. Okay. However, if we rewrite the code, right, with a shared memory, so we can rewrite it like this. Okay, so you can see just like the concept we introduced before, the way to use shared memory is simply try to move the data from the global memory to the shared memory, right, by copying the data. Okay? And to copy the data means you will simply assign the data from the global memory address to a shared memory address, like shown over here. Okay, so this implies a data movement on GPU. Okay, this is how you move the data from the global memory to the shared memory. Of course, you can do the same in the opposite direction, like this, right? Okay, and of course, in this case, assuming we have at the moment, we assume your shared memory is large enough. Okay, so we can move the whole matrix of D to the shared memory S. Okay, and to move that, actually, you can do it in parallel, right? Because remember, all the threads in the thread blocks are shared the same shared memory. Okay, so if you can move, so every thread can take responsibility to move some of the items from D to S. Okay, so in this case, it's a simple case. So we assume, right, we use n squared threads to deal with a matrix, n by n matrix. Okay, so basically each thread can handle one data element. So you can see over here, we simply let each thread to move a single data item from D to S. And at the end, you can see after this statement, okay, if all the threads complete their statement here, then it implies the whole matrix of D are moved to S already. Okay, and a detail here, a very important thing to uh, to look after is remember we said the threads within the thread block may only be executed in parallel logically, right? If they are not within the same WAP. So here we probably we assume that the size of n is larger than 32, which is the WAP size. So some of the threads will not be in the same WAP. Therefore, we have to code this thin threads, right, to create a global synchronization within the thread block to make sure all the threads complete their data movement after this synchronization point. And we need that because if we don't do that, then that means some of the item of S is not initialized, right? Or is not assigned to the value of D yet. Then when the thread access those variable, then you will not be able to read the right value, right? So because for example, right, thread ij will access for example here, right, for thread ij will try to access the data stored on sik and skj, and ik, kj, or ij, they are all different threads. So you have to make sure all the threads have moved the whole matrix has to be loaded to the shared memory before you can do this random access behavior, okay, among the threads. Okay, so we have to apply a thin threads API here to make sure that, okay. All right, and after we do that, you can see we can replace D to S. It seems the code seems the same, but actually the behavior is completely different on GPU because now those S's, right, all the S's to matrix S is only involve shared memory, not the global memory. And you can see that we only touch global memory at the end when we try to assign the result back to the global memory. Okay, so you can see that through the whole process, right? After we utilize shared memory, then each thread only need to access the global memory twice, right? For the input and for the output. So this is the most ideal case. And in between, you can see that there is some data reuse pattern. That's why in the past, we need to require 6 global memory access, but now we only need 2 because 4 of the global memory access are reused and they can use the data stored on shared memory instead. Okay? So you can imagine this code, just this simple modification of the code will accelerate the performance probably around 3 times. So that's significant improvement, right? Run 3 times faster just by utilize the shared memory. Okay, so now you know the concept and exactly how you allocate the shared memory. Actually, the code over here is just there are 2 ways to allocate the shared memory. Okay, the first way is a bit more complicated, is what we show over here. This is a way that we can dynamically, we can dynamically allocate the shared memory at the runtime, because you can see that the size of the shared memory is specified by the 3rd argument in your kernel launch command. Remember, there actually are 4 arguments for the kernel launch command. The first 2 are required, right? Represent the grid size. The later 2 are optional argument for optimization, and the 3rd argument is shared memory size. Okay, so you can specify the size of the shared memory you want to allocate it at the runtime. Okay, but you have to specify that in your kernel function. Okay, in your launch command, and this size again needs to be a static value. Okay, all right, and so since you will specify here, so you can see that the shared memory is declared as an external variable and indicate as a keyword by shared, right? So indicates a variable declared on the shared memory. Okay? And it will be accessible by all the threads within the same thread block. And its size is specified in your kernel launch command. Okay? And once you specify that, then what happened is when the kernel is launched on GPU, before it's executed on GPU, the GPU will allocate the memory size for the thread block. And it will know the amount of shared memory you need for that thread block before he scheduled this thread block to the string processor, right? So that's why you can check whether this thread block can be run on a string processor or not. If there's not enough memory space left, shared memory space left on a string processor, then your thread block will not be scheduled on that string processor, and you will have to wait until some SM or some slot, right, with enough shared memory space for running this thread block. Okay, so what that means is if you try to allocate a shared memory that's if you try to allocate a larger shared memory space, then it may reduce your concurrency on GPU. Okay, and you might suffer from longer scheduling delay on the GPU device. Okay, and another thing is you can see that although you can specify the shared memory size at the runtime from host, but actually on the device, this number is still a static number. You have to decide it and before the kernel can be launched and executed. Okay, so it's not entirely like you can dynamic allocate shared memory on GPU. Okay, all right. So that's why you can observe from this example. Okay. All right. Another thing you need to notice is that in this example, right, we only allocate one variable on the shared memory. So you might think, how about what happens if I want to allocate multiple variable on shared memory, right? And of course, you can do that by just keep writing this line, right? This variable declaration line in your code. Then you can have more variable that is stored on shared memory. Okay. However, those variable will actually points to the same shared memory space. Okay, which means they basically the same symbol. Okay, why is that? So what it means is like this, right? So for example, you have A and B, or even you have C, but no matter how many those variable you declare, all of them pointing to the exactly same address. Okay, and the reason is that for dynamic allocation, right, you can see that the size is predetermined, right? And this size is right, it didn't specify for which variable. In fact, it's for all the variables. So the variable you declare here, they are all just a pointer pointing to the same memory buffer on shared memory. Okay. So again, that's because we all the limitation, right? As from the API, from the interface, you can only describe one size. So that means you can only allocate one chunk of shared memory per thread block. Okay. So actually, it's not recommended to declare multiple variable for shared variable for those shared memory variable. Okay, because they don't have any meaning to it. Okay, so usually people just allocate one variable like this, indicate it's a memory space on the shared memory. Okay, and you have to manage how to use this chunk of a memory on your own, right? For example, if you have array A and array B both want to store on the shared memory, you probably need to know the size of those arrays, and simply say, for example, shared memory 0, right, to the size of array A minus 1 is for array A, and the rest of the space are for array B. Okay. So anyway, you have to manage the offset on your own. Okay, there's no other way around it. Okay, okay, it is confusing, but it's due to the limitation of the GPU. And maybe someday in the future it will change, but at least for the moment, it's still how you could. It's the only way you could use and access the shared memory. Okay? If you want to use dynamic allocation. Okay. All right. So since there's a dynamic allocation, means there's also another way um, to do the static allocation, right? Oh, finally, by the way, for shared memory, as we mentioned, it's only a memory buffer. So this is the correct code. Okay, before we introduce the static allocation, this is the complete and the correct code for using the dynamic allocation on shared memory. And so you can see we only have S, and it has to be a one-dimension array. So the previous code, if you look at more carefully, this is wrong. Okay, the compiler doesn't accept this. Okay, it has to be a one-dimension array like this. So if it's a two-dimension matrix, again, you have to do all the offset computation on your own. Okay, so it's very inconvenient, but it is what it is. Okay, so it needs to be a one-dimension array when you declare the variable for shared memory. Okay, and you have to linearize all the memory usage on your own. Okay, so make sure you linearize in the right way. Okay. Okay, so this is it's more ugly, but this is the correct code for the actual code for our example. Okay. All right, so how about static allocation? It's much simpler, but also much more limited, right? So a static allocation means that you delay the allocation inside your inside your kernel function, right? So basically, you declare that shared variable right within the kernel function. Then this is a static allocation. Okay, and we say it's a static because again, just like again we say within the kernel function, any array needs to be static allocate. So the array, the size of the array needs to be specified at the compile time. Okay, it cannot be determined at runtime. So that's why it's called a static allocation. So it cannot grow, and it needs to be predetermined before running. So sometimes people want to use dynamic allocation. Okay, but if you use static allocation, the code becomes much simpler. Simply write in this way, then you can have a chunk for shared memory. Okay, you can have a variable store on shared memory. Okay, and different from the dynamic allocation. Here, if you declare multiple variable, then they will point it to different memory chunk. Okay, so unlike what we saw before, what we said before for the dynamic allocation, all the variable points to the same address. For a static allocation, because everything is resolved at the compilation time, so it allows the programmer to write it in the normal way that any variable will bind it to a different address on the shared memory space. Okay, so it's easier to write, to understand if you use static memory allocation. Okay, and as a matter of fact, because after we talk about all the optimization technique, you will see that on GPU, all those optimization are pretty ad hoc. Pretty much you have to know exactly how many items are there, how many threads are there, so you can manage the exact mapping between execution and the memory access. So usually the size of the problem or the size of your memory, like size of your array, they are fixed. Okay, so static allocation maybe seems very limited, but as a matter of fact, most of the code, most of the CUDA code can use, will prefer to use static allocation, because you have to optimize your code on a fixed size problem. Okay? So you might ask, well, then what happens if I want to run a program to solve a variable size problem, right? Because the problem size may be an input for my program. I want to write a CUDA code that can deal with any number, any size of problem, right? And the answer for that is usually the problem size is way much larger than the problem size that can be handled by a single, say, a single block or a single kernel or a single grid, right? Because we have limited number of threads can be allocated on each thread block. So usually, anyway, we cannot, put the whole problem to the GPU at once. So usually we will partition the data, right? Partition our input problem to several data chunk and solve them one by one. So the chunk size usually is a fixed size. Okay, so therefore we can optimize and write our CUDA code for that specific data chunk size. Okay, and still be able to handle arbitrary problem size, because no matter what's the problem size you have, you're going to partition it into some fixed size chunk and then try to solve them one by one on GPU. So that's why the CUDA code might seem very ad hoc and specific to certain problem size, but it doesn't limit your program for dealing with arbitrary size problem. Okay. Okay, so anyway, you have two choices here, whether to use a static allocation or the dynamic allocation of your shared memory. Okay. Okay, it all depends on your use case. Okay. All right, so hopefully you get an idea how to use the shared memory, so you can know how to complete your assignment for the lab on Thursday. Okay. Okay, finally is the for the global and the constant memory, and this part is pretty easy because in some way we already introduced it before. Okay, and basically for the global memory, you're going to use the CUDA API from host, right? Because uh, if it's within the if it's within the device, we already saw that you can use simply use the memory assignment operator to move the data from the global memory to the shared memory, or from the shared memory back to the global memory. And between the device memory and the host memory, you have to use the CUDA API, and that is provided for the host. So that's CUDA malloc and the CUDA free we have seen before, right? So I think we don't need to repeat this part, but the most important thing is remember the return value from CUDA malloc is a device pointer. Okay, it's a pointer to the device memory or the global memory. Okay, and because it's returned with a pass by reference method, so the variable you declare here the data type should be a pointer to pointer. Okay, right? And so how can you move, right? The CUDA main copy is to, I think we mentioned this before, right? So you have to, you can choose the memory copy kind to decide whether the direction of the movement, right? And so whether the pointer is a device pointer or host pointer depends on your moving direction. So you need to always be clear whether the pointer you are operating on is a device pointer or a host pointer. And the only way to, or the way to distinguish that is to check which API, right? What API you use to allocate the pointer. Okay. All right. So be careful on that. So that's why most of the time when we name the variable, we will name it by indicating whether it's a device pointer or the host pointer, so we can easily tell whether we write the program in the correct way. All right, this is a bit more complicated example, but but still the same. Basically, what we wrote here is try to copy the data from the device to the host. Okay, and so if you're not interested, you can check the detail and by yourself. So basically, just A and B try to do the copy from the host to the device, and after we add the result, then we move the result or write the result to device pointer C and copy back to the host. Okay. So anyway, this is just a sequence of API code, right? That allow us to move the data between the device and the host. Okay. All right. And finally is the constant memory. So it's similar to the global memory. But however, it's a different memory space. So of course, you need to use a different keyword, right? Like constant to indicate this variable is allocated or binded on the constant memory. Okay? And you can see usually because CUDA main copy is referring to the device memory only. So if you want to copy the data from the host to constant memory, then actually there are a couple of API available. But here we introduce you to use the CUDA main copy to symbol, okay, which is a more powerful API that can move the data around, between all kinds of memory space. Okay, and it can move around on any, it can apply on any memory space because the address is specified by the symbol, right? So it doesn't care where the symbol is at. Okay, so in this case, the symbol is constant data, and we say that constant data is on constant memory, so we can use this API to move the data from the host to the constant memory. Okay. So similarly, okay, if you want to have a texture memory or other memory, you might see the example to use this API as well. But the constant memory, the pointer over here the symbol over here may bind to other type of memory. Okay, so it's a more general CUDA copy code basically. Okay. Okay, but besides the name is different, nothing else is different from how we operate the global memory. Okay, so you can see this is how we could move the data to the constant memory and move it back. Okay, and of course, if it's constant memory, then you cannot override the content. Okay, so that's the big difference. So that means in the kernel function, you can read the data from the constant memory, but you cannot assign value to the constant memory. Okay, that will probably get error during the compilation time or at the wrong time. Okay, anyway, you will cause error. Okay, so that's the difference between constant memory and the global memory. All right, so to summarize it, so you can see that this is all the way we can declare a variable in our kernel function or on GPU, right? If you write nothing in a kernel function, when you declare a variable, then that means it's supposed to be stored on register, unless you have a spell out problem. Okay, you have a spelling problem. Okay. On the other hand, if it's an array, declare without any specifier, then it's a local variable, but it will store on the local memory, not the register. Okay. And if you have to share, then that's share memory device. That means global memory, and constant means constant memory. Okay. And of course, the constant memory needs to be accessed across all the thread blocks. That's why, as shown before, right, the constant memory should be declared outside the kernel function. Okay. Similarly for the shared memory, if you want to use dynamic allocation, then you also need to declare that variable outside the thread block. All right. So and right, each of those memory, because they store at different memory architecture layer, so there's no scope, SS scope, and their lifetime are all different. So it's all up to you how you would like to manage those memory, right? Where should you store those data, and how you want to move around your data across those memory layer in order to optimize your performance. Okay, there's some general principle we mentioned about, so just follow that principle to manage your data, right? If it's constant memory, stored on constant variable, stored on constant memory. If it's reuse data, or you have to modify the data throughout the computation, then they should be stored on the shared memory. Okay, and if it's a temporary variable, then you should use the register, and you have to make sure you don't spell out your register to the local memory. And usually try to avoid local memory as much as possible. Okay. All right, and for the speed, as we said before, right, so you can see register is the fast one, local variable is pretty slow, shared memory can be as fast as a register, global memory is as slow as the local memory, and constant, if it's cache, ideally, and if you reuse it, then it could achieve similar performance to the shared memory and the register. Okay? So basically, make sure you know whether the variable is stored on the on-chip memory or off-chip memory. I think that's only thing that's really matter. Okay. Okay, and the skill, right? So for register, right, every thread you can have many variable, maybe not unlimited, right? Still limited, but you have multiple variable. You could have multiple variable per thread. Okay, but all the variable can only be viewed by a single thread. Okay, same thing for, of course, the local memory or the local variables. Okay? For shared memory, every thread should have a fewer number of variable because the space is shared by all the threads within the thread block. But on the other hand, the visibility, right, is better than the register because all the threads within the block can see the variable as well. And finally, the global variable, right? So the global variable, there's only just one across the whole grid, through the whole kernel, but it will be visible for all the threads, right, globally. Okay, so they have their own properties. Okay, so that's it for the hardware architecture. Okay, so hopefully you know all the detail of or all the hardware architecture, so that will help you to understand the optimization we're going to talk about in the next lecture. Okay. All right, so since we have only 10 minutes left, so I think we can reserve the time for a question. Okay, and we will start talking about optimization in the next lecture. Okay, which is the most important lecture for CUDA, and that's, well, all the information you need for optimizing the code of your homework.